Hello and welcome back to m200 lecture series for Cañada College. We are using PowerPoint presentations from Mario Triola's textbook, Essentials of Statistics, 5th edition. My name is Ray Lapuz. We are in Chapter 8, Hypothesis Testing. In the first few chapters of the textbook, we discussed descriptive statistics. In chapters 4, 5, 6, we went over probability and probability distributions, and in chapter 7, we began our discussion of inferential statistics. So inferential statistics is the use of data to make inferences or conclusions about a population. Now we've already gone over one prong of inferential statistics, and that is the confidence interval. Now we will discuss hypothesis testing. The main idea in this chapter is to develop procedures to conduct hypothesis tests for claims made about a proportion, a population mean, or population standard deviation. Let's take a look at some examples of hypotheses that can be tested. In genetics, we can check to see if an X-sort method would actually allow couples to increase the probability of having a girl. In business, we can check a claim that the majority of people have heard of Kindle as an e-book reader. And in health, we can check the idea that the average body temperature for humans is 98.6, or can it really be lower at 98.2? A word of caution when conducting hypothesis tests described in this chapter and the following chapters. We want to make sure that we follow the procedures and also consider the context of the data, the source, and the sampling method used. Section 8-2, the basics of hypothesis testing. The main idea here is to develop a procedure for hypothesis testing. In the textbook, they spoke about 8 steps. We can really break that down to 3 major steps, and it should be as follows. The first step is about making a claim. We want to be able to identify null and alternative hypotheses from a given claim, and then express them in symbolic form. The next step is to test the claim. So we would calculate some test statistic and find some p-values, and then from there make a decision. And then the last step is to draw your conclusions about your claim. So we want to be able to state our conclusion in simple and non-technical terms. Let's take a look at some definitions. A hypothesis is a claim or statement about a property of a population, basically about a population parameter such as proportion, mean, or standard deviation. A hypothesis test is a procedure for testing this claim. We've had this rare event rule introduced to us earlier on. Let's take a look at it again. If, under a given assumption, the probability of a particular observed event is exceptionally small, we conclude that the assumption is probably not correct. And in these cases, we would reject our given null hypothesis. Let's take a look at what a null hypothesis is. A null hypothesis is a statement that a value of a population parameter is equal to some claimed value. So null hypothesis should be related to a statement of equality. The null hypothesis is the exact statement that we will be testing in our hypothesis test. We test the null hypothesis directly to say that we're going to reject or fail to reject the null hypothesis. The alternative hypothesis is the exact opposite of the null hypothesis. The symbolic forms for the alternative hypothesis would contain a not equal to symbol or a less than or a greater than symbol. One important note about forming your own claims or your own hypotheses: if you're conducting a study and you want to use a hypothesis to support your claim, then your claim must be worded so that it becomes the alternative hypothesis. Here are the first 3 steps of identifying the null hypothesis. First, we would identify your claim or a hypothesis that you want to test, and we want to put that in symbolic form. Step 2, we want to find the logical opposite of the symbolic form. And step 3, we want to decide which of the first 2 statements given in steps 1 and 2 will be your null hypothesis and which one will be your alternative hypothesis. Remember that your alternative hypothesis will have a less than, a greater than, or a not equal to symbol. And your null hypothesis will have a condition of equality. Let's take a look at an example. Assume that 100 babies are born to 100 couples treated with the X-sort method for gender selection that is claimed to make girls more likely. So let's say we collected some data. We observed that 58 girls in 100 babies were born. So our claim should be that the proportion is bigger than 50%. The opposite would be less than or equal to. And so we can write our null hypothesis as P is less than or equal to 0.5, and then our alternative hypothesis would be P is bigger than 0.5. Our step 4 is to select a significance level. Most of the time this will be given to you. If a significance level is not identified for you in the problem, then we should assume that it's 0.05. Significance level will be denoted by alpha, and this is the probability that the test statistic will fall into the critical region. Some common choices, as already mentioned, are 0.05, 0.01, and 0.10. Our 5th step is to identify a test statistic and determine the distribution that we will use. So here we have 3 scenarios. We have a proportion, we have a mean, and a standard deviation. Now, the proportion will be a z distribution, and our test statistic is given on the right. Our mean will depend on whether or not you know the population standard deviation. So that breaks down to 2 more different scenarios. If we do not know sigma, we will use what's called the t distribution. And if we do know sigma and the population is normally distributed, we can use the normal distribution z. For standard deviation, we will use the chi-square distribution. The test statistic is a value that we're going to be making a decision about the null hypothesis. And we convert the test statistic basically into a score that would align with the distribution that we're using. In step 6, we would find the test statistic and or the p-value. Actually, for us, we were going to be finding both in most cases, and we can either choose the p-value method or the critical value method. Let's go back to the example with our XSort method for gender selection. Preliminary results test that we found 58 girls and 42 boys out of 100 couples. So we're going to use the given claim and the preliminary results to calculate the test statistic. And we're going to use the format of the test statistic, and since this is a proportion problem, we will be using the normal distribution. So here are our null and alternative hypotheses. So we're going to work under the assumption that the proportion P is equal to 0.5. Our P hat, this is our proportion for the sample that we have, is that 58 out of 100 were girls. So P hat is going to be 0.58. Our test statistic formula will yield a 1.6. So as a z-score, this is really not so unusual. It's within the realm of 2 standard deviations from the mean. And so we're looking at this as probably not that big of a deal. So at first glance, we can say this does not seem to support the claim that it actually increases the chances to be over 50%. It is 58%. It's a little bit over 50%. But the question is that, is it really significantly over 50%? And that's what the hypothesis test is testing. Let's go back to some more procedures. There are 3 types of tests that we would do for hypothesis tests, and it depends on the tail. The tails in the distributions are the extreme regions bounded by the critical values. Determination of the p-values and critical values are what affects whether the critical region is in 2 tails or left tail or right tail. So a 2-tail test would involve a not equal to symbol for our null hypothesis. So the idea is that our tails are distributed between the left and the right side, so that if our value, our test statistic, would fall in the tails, and the tails would be called the critical region, then we would reject the null hypothesis. That's the rare event rule. If it's not, then we cannot reject, we fail to reject the null hypothesis. 1-tail test, either on the left side. If your alternative hypothesis has a less than symbol, then we would be looking at the critical region on the left side. If your alternative hypothesis has a greater than symbol, then we will be looking at a right tail test, and we would reject values on the right side. The p-value is called a probability value, and it's a probability of getting the test statistic at least as extreme as one of the representing sample data. So if the critical region is on the left tail, the p-value will be on the left side. And if the critical region is on the right, the p-value is going to be the area from the test statistic to the right side. Now, the tricky part is that a critical region is in 2 tails, then our p-value is going to be twice the area and the tails beyond the test statistic. Our calculator would be able to help us find the p-values rather quickly. So the p-value, the null hypothesis is rejected if the p-value is really, really small. This is to say that the test statistic is far away from the mean or far away from the middle. In our example, we found that the test statistic was 1.6. If we take a look at the test statistic, z-value of 1.6, we can find the area to the right of that, since this is a right tail. And the p-value would be 0.054. Here's a little flow chart of finding the p-values, but we can skip over that. The critical region is the part of the graph that would cause you to reject the null hypothesis if your test statistic would be in there. The critical value is a value that separates the critical region where you would reject the null hypothesis from the other region. And the critical value depends on the nature of the null hypothesis. In our example with the XOR baby, we were testing if the proportion was greater than 0.5, and so we would be looking at a right tail test. With a 0.5 significance level, we would find our critical value to be 1.645. With that, we would shade in the critical region to the right of that number. A word of caution, especially when we move into the next section. Our p-value is a probability of getting a test statistic at least as extreme as one of the representing sample data. Our p symbol is the symbol that we use for population proportion. So I generally like to use PV for the probability value. In step 7, we want to make our decision. So there's a simple decision-making process if you're using the p-value. If you're using the p-value, you simply compare your p-value with the given significance level, alpha. If the p-value is less than or equal to alpha, then you reject the null hypothesis. If the p-value is greater than alpha, then you fail to reject the null hypothesis. If you're using the critical value method, what you would do is you would draw your graph with the critical region and the critical values, and then if your test statistic falls within the critical region, then you reject the null hypothesis. If the test statistic does not fall within the critical region, then you fail to reject the null hypothesis. Back in our example, we found that our test statistic was z is equal to 1.6 and the p-value is 0.0548. If we were using the p-value method, we would compare this with alpha at 0.05. We'll see that the p-value is slightly greater than alpha. If we were to use the critical value method, we'll see that the critical value is 1.645 and our p-value or our test statistic is 1.6. So that does not go into the critical region. We are a little bit to the left of that. In either case, we would conclude that we would fail to reject the null hypothesis. One, because either p-value is greater than alpha, so we reject the null hypothesis, or two, since our test statistic does not fall in the critical region, we would fail to reject the null hypothesis. In either case, we would come to the same conclusion. Now the last step is to restate your decision using non-technical terms. So we want to be able to state it without using words like null hypothesis, p-value, significance level, alpha. Those are all technical terms. So we want to use non-technical terms and refer back to the original claim. There is a nice flowchart found in an older edition of your textbook, but you can certainly use this, where you get to use a wording, a set of words, to fill up your conclusion. First, it asks if your original claim contains a condition of equality. And whether or not it does, we have a second question if we rejected the null hypothesis. And then we have a set of 4 statements to choose from. Let's finish our example. For this, we've found that our null hypothesis was p equals 0.5. Our alternative hypothesis was p is bigger than 0.5, and that is our claim. And so because our claim does not contain a condition of equality, we would go to this next decision box. This box is asking if we rejected or failed to reject the null hypothesis. In our case, we failed to reject the null hypothesis. So in our decision-making process, we would say there is not sufficient sample evidence to support the claim that. And then what we would do is just restate our original claim. So our conclusion would be there is not sufficient evidence to support the claim that the XORT method is effective in increasing the probability that a baby girl will be born. So we want to just state a word of caution that when we're doing a hypothesis test, we're rejecting the null hypothesis or failing to reject the null hypothesis. I notice that the word null hypothesis is not included in our non-technical term. Another word of discrepancy. Some textbooks use the word accept the null hypothesis, but since we are really not proving the null hypothesis, we are trying to reject the null hypothesis. And so not rejecting doesn't necessarily mean accepting. Let's take a look at types of errors that can happen. This is statistics and probability after all, and so we're always bound for some error. A type 1 error is a mistake of rejecting the null hypothesis when it's actually true. Now that can happen, and this error is represented by a probability of alpha. So if your significance level is 0.05, then there is a 5% chance that we would be rejecting the null hypothesis when it was actually true. A type 2 error is an error of failing to reject the null hypothesis when it's actually false. And so here's a nice table that describes the type 1 and type 2 errors. Let's take a look at our example, and let's backtrack to the very beginning, assuming we didn't know our conclusion. Identify the type 1 or type 2 errors that could happen here. A type 1 error would be the mistake of rejecting the null hypothesis when it's actually true. We can conclude that the probability of not having a girl is greater than 50%, when in reality it is not. Or a type 2 error is a mistake of failing to reject the null hypothesis when it's false. There is no evidence to conclude that the probability of having a girl is greater than 50%, but in reality the probability is greater than 50%. And here's one final page to try to control your types 1 and type 2 errors. For fixed alpha, an increase in sample size will cause a decrease in the type 2 error probability. For any fixed sample size n, a decrease in alpha will cause an increase in type 2 error, and conversely an increase in the type 1 error will cause a decrease in the type 2 error. So if you want to decrease both type 1 and type 2 errors, you simply need to increase your sample size. Alright, that's the end of section 8-2.